So there'll be a little bit missing at the start. Sorry. Um, so I mentioned yesterday that all the other connectives that I introduced can be in fact defined in terms of only these three. And in fact, any connective that you can imagine with as many variables as you want can be expressed in terms of these three. And what I'd like to do is I'm not going to give you a formal proof. Um, if you look up the exercises, this is an exercise that you've been assigned in the list. It's a harder exercise, obviously, but I'm sort of going to solve it here. I'm not going to be very formal. I'm going to give you the basic idea, and I think this is sufficient to really get it. So the term completeness means exactly that. So if you take any truth table, so imagine it, let's say you have 12 variables and you put all the possible values for your 12 variables, and you just choose arbitrary values for your connectives, for your connective, sorry, um, just true or false anywhere you want. Okay, then this is completely arbitrary table. You can actually express it in terms of and or not, and that's what I would like to illustrate here. So I'm not going to give you a general proof. I'll do it for an example, but I'll explain it in a way that you should be able to figure out how it works for any other table, for any connective. Okay. So or and not are sufficient to express any possible truth table. And you have to throw in the constants true and false to be very, very precise, because the table that contains all true or all false, you'll need that. Okay. But so here's my example. So this is an arbitrary truth table. So you could change the values here in the right hand column. You can take whatever you want. It makes absolutely no difference what you put here. Okay. I called it A, and it has three variables, PQR. And as we discussed yesterday, this is the list of all possible truth values. I started with true, 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 and put them in lexicographic order, assuming true comes before false. It doesn't matter if, let's say you're doing a test, it doesn't matter in which order you put them. Um, but keep in mind that if they're all jumbled up in some really weird order, it's going to be harder for me to verify what you're doing. So always try to be nice to whoever's marking, right? So here's a arbitrary table, truth table, and I'd like to find an expression involving or and not that will give us exactly this truth table, which will be logically equivalent to this. Okay, so the starting point is to look in the table where this this connective is true. Okay, so where is it true? It is true for values true, true, true for PQ and R. It is also true for values true, false, false. It is true for false, true, true. And it is true for false, false, true. So there are four rows where it is true, and I wrote them down here. So it's true, 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 false, 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 true, true, false, false, true. So once I know that, then I know the table, right? So the rest are false, obviously. Okay. So let's see what that means. So, and this is really the key point. Once you understand this, basically you've understood the whole proof, the whole thing. Okay. So I'm going to find an expression which involves only or and not, which is true exactly when PQR is true, true, true. So I want an expression involving PQR built with or and not, which is true only when all three are true. Now, remember what I said about and? It is true in only one case when all the variables are true. So it's actually pretty easy to come up with this expression, right? P and Q and R, okay? This will be true precisely when all three are true, okay? Um, I didn't put brackets here. I should have put brackets, but it turns out, and you can think about it, that it makes no difference in which way you bracket this. It's associative, so we just drop the brackets, right? So I could have written P and Q in brackets and R, but it'll turn out to be exactly the same thing. So the only way this is true is when all three are true. Okay. Next, I'm going to move on to the second triple from my table, which was true, false, false. Okay, and I'd like an expression which is true precisely when P, Q, and R take these values. So it's the same trick, right? Except that now I have two falses. So I'm going to flip the two variables by negating them. Okay, so if I take P and not Q and not R, how is this true? P has to be true, not Q has to be true, not R has to be true. In other words, Q and R have to be false. Okay, so this expression, again, notice that I'm not using or at this point. I'm just using and negation. So this expression here will be true precisely on these three values and nothing else. That's it. Okay. If you see where I'm going with this, you can probably figure out all the rest of the thing, right? The slide. So for false, true, true, I want an expression which is true only for these three values. Well, not P and Q and R. This will be true precisely for these three, okay, for this triple. And finally, false, false, true. This will be true. If I look at this expression, it'll be true exactly for these values of P, Q, and R, right? So not P and not Q and R, okay? So these are my four triples from my table where my arbitrary connective was true, okay? And I found for each one of them an expression which lights up true precisely for that triple. Now I want to put them together, and you can probably guess what it's going to be. You're going to take the disjunction of all these four, okay? So if you take the or of these four things, when is it true? Okay, so look at this expression here. This is the disjunction or of all the four expressions we had, okay? When is this true? When at least one of them is true, okay? And when is one of them true? It's true exactly on those four triples that we took from the table, okay? So the how is yeah, sorry, yeah, coffee. Better. Um, so this lights up true for true, true, true. This lights up true for true, false, false. This one lights up true for false, true, true. And this one lights up true for false, false, true. So this will be true precisely on those four triples that we got from the table. In other words, this is an expression which will give us exactly what we had. Okay. So if you understood what I just did, it's exactly the same principle for any table, right? So if you take any table, look at those rows that will light up as true. You can find an expression involving only ands and negations that will light up as true precisely on this tuple. And then you take the disjunction of all this, and that's it. Okay. Um, I don't think I want to go further than this on this topic. Um, and in fact, that's pretty much the end of what I wanted to do today. So I said it was short, it is short. So this is it for propositional calculus, the basics. On Thursday, I don't think I'm going to start any new material per se, but I will give you a little fun talk on infinite sets. I think this could be interesting. So we talked about finite sets in chapter 2, and I mentioned briefly when is a set finite and infinite. I'm gonna just sort of uh, jam on infinite sets and have some fun with that. There'll be a little itty bitty question on the first test about that, but just to see that you were paying attention. So it's not material from discrete math per se. It's just for fun. And then next week I'll continue chapter 1, where we've reached 1.4. So we're going to start adding stuff to our logic, which is very basic at this point. It doesn't do much. And so that's it. Are there questions, comments, anything of a general nature at this point?